Okay, so yeah, I'm Takahiro Sagawa from University of Tokyo, and today's topic is topological characterization of nonlinear dynamics. So first, let me make an excuse about my topic. So this is a chemistry session at workshop on stochastic thermodynamics. So I wanted to find some connection between my topic and this session. Actually, so the chemistry is chemical reactions are typical nonlinear dynamics. And also, I think there should be a deep connection between topological phenomena and stochastic thermodynamics because topology makes some dissipationless current and stochastic thermodynamics cares about some irreversibility like entropy production. So I hope to discuss some possible connections in this opportunity. And the references of my talk are these papers. And the main main player is Kazuki Sone. He's my former student. Okay, so this is a background. Uh, Topology in physics. Historically, topology was topological phenomena were discovered in quantum materials. The most famous one is the quantum Hall effect, and more recently, topological insulators attracted much attention. And much more recently, the concept of topology has been extended to classical systems. And for example, this is a mechanical lattice, and we can observe some unidirectional edge waves, sound wave along the edge of this lattice. Also, it has been argued that some waves on Earth have some topological origins. Also, this is our work, our previous work, and we found some exotic topological phenomena, and that can be implemented in chiral active matter like these bacteria. And also, there are several uh, topological phenomena in classical stochastic processes, including biochemical networks. So this is a pioneering work by Suri Vaikuntana-san, and this is about some topological edge mode in biochemical signal transduction. Recently, we have extended the work for more general situations, and we have also discussed another topological aspect of one-dimensional classical stochastic processes. And let me briefly review the most fundamental concept in topological physics. That is the so-called the bulk edge correspondence. Roughly speaking, it states that the bulk topological number is corresponding to the edge dissipationless current. The bulk topological number is defined on the wave number representation. For example, this is a Chern number for the two-dimensional system. In the one-dimensional case, it is represented as a winding number. And at the edge of the system, in the open boundary condition, so there are localized states along the edge, and they have gapless dissipations. And the most interesting feature is they are backscattering free. This is a kind of dissipationless current. And they are also robust against disorder. So this is a very unique character of topological phenomenon. And the focus of today's talk is nonlinear dynamics. There are many nonlinear phenomena in nature, like biological oscillators. This is a firefly, and active matter and chemical reactions. Also, there are artificial systems like photonic systems and ultraviolet atoms and electric circuits. But in the previous studies, most of topological phenomena were found in linear systems, and the general concept was discussed only in linear case. So my question is, what about topological phenomena unique to nonlinear systems? And is it possible to define topological invariants like winding number or Chern number that can characterize nonlinear systems? Okay, so these are today's topic. First, I would like to briefly review our first result about topological synchronization. This is a topologically originated synchronization of nonlinear oscillators. And next, I will go to a more general theoretical part. And that is about the nonlinear Chern number and topological to chaos phase transition. Okay, so let me start with the topological synchronization. So the basic idea is very simple. So there are many famous nonlinear oscillators and there are synchronization like Kuramoto model and Stewart-Randall model. And we have introduced the topological linear coupling between these nonlinear oscillators. So this is a nonlinear term known as the Stewart-Randall model, and this is a topological linear coupling. So basically, this coupling can be arbitrary as long as it is topological, but we have demonstrated by several special simple models like QWZ model. And we found that by introducing this topological linear couplings, there is a new topological synchronization phenomenon. So where the edge, only at the edge, the oscillators are synchronized, but in the bulk, oscillators are chaotic. So this is analogous. This is analogous to the bulk edge correspondence in the quantum materials, but this is completely classical and nonlinear phenomenon. Okay, so this is a numerical demonstration. So please look at this frequency mode. So only at the edge, they are almost white and they are synchronized. But at the bulk, these oscillators are very chaotic. So we have quantitatively evaluated this phenomenon by the Lyapunov analysis. We found that the Lyapunov vectors with smaller Lyapunov exponents in this region are corresponding to the edge localized mode. So this represents the edge proportion of the Lyapunov vector, and this edge modes are corresponding to this smaller Lyapunov and very negative Lyapunov exponents. On the other hand, these chaotic Lyapunov exponents, positive Lyapunov exponents, are corresponding to the bulk mode with a very small edge proportion. So this shows this is actually true for general situations. And one application of this kind of topological synchronization is that we can design arbitrary synchronization pattern by using the topological nature. For example, we can introduce the defect. In this case, these UT are the defect. They are damped oscillators. They don't move. And then we will see that only at the edge of these defects, the oscillators are synchronized. So this can happen for arbitrary configuration of defects or arbitrary configuration of edge. And this is a very special nature of topological synchronization. And this will not happen if the coupling is non-topological. Okay, so this is a brief overview of the first part. And next, I'm going to more theoretical concept of nonlinear topology. So, okay, so in the linear case, it is known that the topological invariant is given by Chern number. This is a kind of a magnetic field on the Brillouin zone. And this is based on the wave number representation based on the Bloch theorem. So the problem is how to extend this Chern number to the nonlinear region. So this is our first question. So there's a relevant previous work very recently published here. And inspired by this work, we have introduced the nonlinear eigenvalue problem, and we have defined the nonlinear topological invariant that we named nonlinear Chern number. So the idea is very simple, and we just extend the linear eigenvalue problem to the nonlinear case, but this is very hard to solve. And then we introduce the Chern number in the same form, almost the same form as the linear case, but we now have a new parameter that is amplitude of the wave function. This is irrelevant in the linear case because in the linear case, we can consider arbitrary amplitude, but now the topological number is dependent on the amplitude of the wave function. So, and this is a more detailed description of the nonlinear Chern number. So this is the original linear equation, and we introduced the Bloch ansatz. This is a kind of plane wave ansatz. So this is a theorem in the linear case that is known as the Bloch theorem, but we don't have such a theorem in the nonlinear case. So we put this ansatz as a kind of assumption, but we can explicitly check that this assumption is satisfied for a very broad class of concrete models. And then we fix the amplitude that is written as double, and we define the nonlinear Chan number that is dependent on the amplitude. Okay, so this is a definition. So, but this definition itself is not so meaningful when it doesn't predict some physical phenomena. So our main focus is not the definition itself, but our main focus is how this definition can predict a unique topological phenomena in nonlinear systems. So for that purpose, first we need to clarify the concept of nonlinear topological edge mode. So this is not a so trivial concept. So in the linear case, only in the topological phase, we have a localized edge mode. And in the trivial phase, we don't have any edge mode. But in the nonlinear case, we found that even in the non-topological phase, we have a kind of edge mode, but that is anti-localized. So in the topological phase, so the edge mode is localized, but in the non-topological phase, the edge mode is anti-localized. So, but we can show that this anti-localized mode can be adiabatically eliminated. So we can erase this by a continuous deformation of the model. So in that sense, this anti-localized mode is not topological, and we can just erase this by continuous deformation. So we can define the nonlinear topological phase as a phase that is adiabatically disconnected to linear trivial phase. So we can say that only this localized mode has the topological origin. So another important aspect of nonlinear topology is that we can find topological nonlinearity induced topological phase transition. So in the linear case, the amplitude is an irrelevant parameter. So at any parameter, at any amplitude, the phenomenon is completely the same. But in the linear nonlinear case, if we enhance amplitude, we can observe some phase transition from the trivial phase to the topological phase, or vice versa. So this is a unique phenomenon to nonlinear topological dynamics. Actually, so in this region, before the transition, this is adiabatically connected to the linear case. So essentially, this is the same as the topological, linear topological phenomenon. But after the transition, we can find a new topological phase, and that is disconnected to the linear topological physics. So we, in a simple analytically solvable model, we explicitly found that this kind of phase transition actually appears in nonlinear dynamics. And we have also analytically shown that the bulk edge correspondence is satisfied even after this transition. I mean, the nonlinear Chan number can predict this nonlinearity in this topological phase transition. For example, if we calculate the nonlinear Chan number analytically, and if we calculate independently, we can calculate the edge mode, and we can see that they are completely the same, and at the same point, their behavior becomes different. So this is our main result of this nonlinear bulk edge correspondence. So this is a model, and we don't go into the detail, but this is a kind of typical model of linear physics, but we have introduced nonlinear term in this square form. And we can analytically obtain the topological phase diagram like this, and we can see there is a nonlinearity induced topological phase transition, for example, here to here. And we have also proposed experimentally accessible way to observe the nonlinear phase transition. So this is a model, lattice model. And for example, we shed light to only the edge of this sample. And in the linear, in the trivial phase, we can see that the edge excitation propagates to the right direction, and this is just the ordinary behavior of the excitation. On the other hand, in the topological phase, the edge excitation cannot propagate, almost can't propagate, and stays around the edge. So this is a topological, this has a topological origin around here in the phase diagram. So this difference is our experimental observable behavior of nonlinearity in this topological phase transition. Okay, so this is the second part. And finally, I'm going to the last part that is about the topological to chaos phase transition. Okay, so this is a bifurcation diagram of chaos. So in this case, so this represents the spatial chaos of the edge mode. For example, in this non-chaotic region, this is a position dependence of the edge mode, and this is just a localized edge mode. So this is corresponding to the non-chaos region of this diagram. On the other hand, if we increase the nonlinearity very strongly, then we have a spatially chaotic edge mode like this. So this is corresponding to around this region of this diagram. So what we have found is that in the weakly nonlinear region, so the situation is the same as the linear physics, but in the intermediately strong nonlinearity, we have the nonlinearity-induced phase transition, as we have shown in the previous paper. So, but in the further strong chaotic region, in the further strong nonlinearity region, we see the spatially chaotic zero mode. So this is the origin of the breakdown of the bulk edge correspondence, because the bulk edge correspondence is relevant to only this kind of this kind of mode, and this becomes unstable after the bifurcation. So, so in this sense, so this diagram shows the topological nature of nonlinear dynamics in a unified way to a weakly nonlinear dynamics and nonlinearity in this phase transition that is a strongly nonlinear region, and in the more strongly nonlinear region, we have the breakdown of the bulk edge correspondence and the bifurcation and the chaos transition. So to show this, we have chosen a simple one-dimensional model that is called the SSH model. So that is a one-dimensional topological model. And this is a equation of the nonlinear SSH model, and we can derive the dynamical system of zero mode from this equation. And this dynamical system describes the edge mode, and from this we can show this bifurcation diagram. Okay, so and this is an outline of the proof of the bulk edge correspondence. So in the two-dimensional case, in the case of the Chan number, the proof is very complicated, but in this one-dimensional model, the situation becomes much simpler. So in this model, I'd like to show the outline of the proof of the nonlinear bulk edge correspondence. In the linear case, the winding number, that one-dimensional topological number is given by this expression, and the dynamical system of the edge mode is given by this. But in this case, everything is linear, so this is just a exponential damping of the edge mode. On the other hand, if we introduce the nonlinear term here, then the nonlinear winding number becomes like this, and the dynamical system of the edge mode becomes nonlinear. But if we look at the edge around the edge around here, so we can see a kind of renormalization of the parameter from the linear case to the nonlinear case. By using this kind of renormalization, we can analytically show the bulk edge correspondence even in the strongly nonlinear region. So that is the outline of the proof. Okay, so in terms of this bifurcation diagram, so for example, here is the topological region, and in this region, the dynamical system becomes like this. And in this diagram, starting from here, the H mode will reach this position. This means the localization of the H mode. On the other hand, in the trivial case, starting from here, the H mode comes from here to here. This represents the anti-localized mode that is adiabatically connected to the trivial phase. And at the phase transition point, here is just this flat H mode. Okay, so and after the bifurcation, so we have this kind of oscillation that is no longer topological or even not trivial, but this is a kind of a purely nonlinear behavior. And even in the much stronger nonlinear region, we will see the spatial chaos of the H mode. So this spatial chaos and the periodic bifurcation will lead to the Barclay's correspondence, because the Barclay's correspondence is only relevant to this curve. And this curve becomes unstable after the bifurcation. Okay, so this is the summary of these three topics. And first, I talked about the topological synchronization. So this is a rather numerically based observed phenomenon. And we have numerically observed that there is a topologically originated synchronization of nonlinear oscillators, where the bulk modes are chaotic and the edge modes are synchronous. And this is this kind of edge synchronization is very flexible, and we can design any pattern of synchronization like this. And in the more theoretical part, so we have introduced the nonlinear Chern number. But our main focus was that this Chern number actually represents some real physical phenomenon, and we have shown that this nonlinear Chern number can predict the nonlinearity-induced topological phase transition. And we have also shown that in the further strong nonlinear region, we will see the chaos transition and the bulk edge correspondence is broken. So this is based on the one-dimensional model, but our argument is essentially very general. So this kind of behavior is independent of the dimension of the system. Okay, so this is the end of my presentation. Thank you very much for the attention.